particle in any polarization basis. Like if you ask it, are you 45-degree polarized, or are you right circularly polarized, or whatever question you ask, if you ask the same question, the same measurement, the same to the other particle, then it will give a perfectly correlated answer if your experiment is whatever. And that doesn't matter how far the two parties doing this measurement, these two identical measurements, are apart from each other. They could be at opposite ends of the universe or the galaxy. They will always have perfect correlations unless something, well, decoheres the correlations in between the two particles. And that's what I call this spooky action. So why would, if I make a measurement here and the other person doesn't really know which measurement I'm making. So let's say I ask the photon, are you horizontally polarized? The other person doesn't know if I'm asking this question. I could just as well ask, are you horizontally polarized or anti-horizontally polarized? And no matter what I ask here, if this person asks the same questions, you will get the same or very correlated result. And so it seems as if there was some information going from this particle to the other one, and that's what Einstein called the spooky action at distance. But really it's just, you know the states beforehand, well, just from an operational quantum mechanicist's, quantum physicist's point of view. It's just updating your knowledge. First you know the state, so you know there have to be perfect correlations, and then you make a measurement, so you gain more knowledge. And this way you gain knowledge about what the other particle is supposed to look like now, about the measurement outcome you will maybe have on the other side. And that's all there is to entanglement, unless you ask questions like, what's really happening? So, still, Einstein was bothered by this concept of the spooky interaction at distance, and he and Podolsky and Rosen came up with this EPR that everybody since then is talking about, that what they claimed is that, okay, every reasonable physical theory has to fulfill two concepts. It has to be local, so nothing happens quicker than this, no information is transferred faster than the speed of light, and measurement outcomes are predetermined by properties of the physical system, or by actual physical properties. And then later on, Bell showed, well, if you assume that, then you get this inequality, this famous Bell inequality. Every theory that sticks to these two concepts has to fulfill. The problem is, one theory violates this inequality. So if you have entanglement, if you have good source, then in principle you can cook up an experiment where you violate this inequality and show in the lab that no such theory following the two concepts of reality and localism at the same time can be right. They cannot explain what we see in the lab. So nature, often people then say nature is non-local. That's going too far, it's not local and realistic. So, and basically this splits the physicists into two camps. Like the one say, okay, physics is not real, and the other people say physics is non-local. I'm more in the non-real side, but that's a matter of taste, I suppose. Nature is not realistic and local at the same time. That's what we know from experiments. But even experiments, I said earlier that if you have entanglement, you have perfect correlation between the two particles, and that's what Bell actually put into the derivation of this inequality. And the problem is, in nature, you never have perfect correlations. In the lab, if you go to the lab, you perfectly prepare your state and everything, and then you usually get this famous fidelity that you measure then with the perfect state, and it's never 100%. It's always less than perfect. So you cannot assume, if you, like as Bell did in a theory, that okay, assuming we have perfect correlations, we can get that and that, because that's just a wrong assumption. So later on, people came up with more realistic Bell-type inequalities, the CHSH and the CH inequality, And those you can actually measure in the lab, but still under some conditions, because even those rely on some assumptions. If you test them in the lab, if you just take this inequality and go to the lab and measure some results and put them into the inequalities, you will not violate them, usually. Because typically the detection efficiencies, the collection efficiencies, if you send one photon from one side to the other, you won't catch them, all these photons, and couple them to the detector. So you have limited efficiencies, and that directly degrades the correlations you put into these inequalities. Unless you assume, for example, this fair sampling hypothesis that the detector doesn't really care what the quantum state of my system is. That's the fair sampling assumption. Or the fiber which I try to shoot into doesn't really care what the quantum state of my photon is. So that's the fair sampling assumption. And until a few years ago, that in every Bell experiment that was done, this fair sampling assumption was made to actually violate these inequalities. It's a reasonable assumption, but if you do not want to believe in quantum mechanics, then you can find a loophole evading this measurement result, this violation of Bell inequality. And well, it's the fair sampling assumption. Then there's other loopholes. For example, okay, if I make a measurement here and I choose a measurement there, if this person gets to know what this person does, then this again opens a loophole, because this particle could kind of already know what he's supposed to say at this measurement apparatus and so on. So that's various locality loopholes and so on. So you have to separate your measurements such that no information about choosing this setting can get to the other side in time to reach the particle before I measure it. And over the years, these loopholes have been closed one by one, more or less. So far, there has not been a single experiment closing all the loopholes at the same time. And probably, even if you do such an experiment, somebody will come up with a new loophole at some point. But we can only do the best we can. And well, one of the first loopholes that was addressed was this locality loophole of that this party does not know, should not know what this party is doing over here. And this was already more or less closed by Aspect in the early 80s, and later on a little bit more conclusively by Gregor Weiss and others in the group of Entanglement in Vienna. And the idea is just that, okay, you have, that's just a space-time diagram, so distance and time. So if you have a source and it emits photons with the speed of light, then it would just go on at an angle of, go out at an angle of 45 degrees here. Here in this experiment it was such that in the beginning the photons were just delayed in a fiber coil, so the photons stayed at the same place for some time, and then they were sent out to different parties. And that was made such that if I choose my setting here on Alice's side, or on one side of the experiment, then this information, what Alice does here, can travel maximally with the speed of light. So it is fast, not faster than that. So it cannot reach this point here in time where I make the decision what to measure on Bob's side. And that's all what this experiment is about. So you separate these events such that no information from choosing one setting here can reach the other side in time to have any effect. And this, well, the Bell inequality using this experiment was violated really well. So this closed the locality loophole with photons. Unfortunately, the detection efficiencies in this experiment were pretty low, so it definitely did not close the detection loophole at the same time. The detection loophole, on the other hand, was later on closed by the Rainer group in 2001. They did not use photons, but ions in a trap. So they had two ions in an electromagnetic trap. And also with ions, like with photons, we always talk about polarization. So photons polarize horizontally vertically, the other photon has the same polarization or entangled polarization. And with the two atoms, it's just spin. So we have two atoms entangled in spin. Or in a superposition, you can also entangle them. One atom is in a superposition of two atomic levels, and the other is also in a superposition of two atomic levels, and you can create different states here, and so you can generate entanglement in this way. And those guys created entangled states of two ions between the internal levels of two ions, and then performed Bayer measurements. So they generated these two ions in two separate spots, applied all kinds of lasers to it to generate the state, and then shown a laser edits to read out the correlations of those two ions with really high efficiency, much higher efficiency than you could have in photonic experiments. And this way they were able to violate Bayer inequality without the fair sampling hypothesis. So they closed the entanglement, the detection loophole with this experiment. The problem is that those two ions were directly next to each other, so this experiment did definitely not close the locality loophole. If you want to close the locality loophole, then you have two choices. Either you take a photonic experiment where you can easily close the locality loophole and use better detectors to close the detection loophole, or you have two ions and put them further away such you can close the locality loophole at the same time and have this high detection efficiency. So far the photons won, so they were the first to close both loopholes at the same time. So they had, in this case, in this experiment, they actually didn't have the detectors too far away from each other, but they arranged the whole experiment such that the fair sampling hypothesis did not apply. Oh, sorry. I mixed that up with the next one, but in a different experiment. So in this experiment, they just closed the detection loophole. So they did a usual bad experiment, so they generate the entangled source, then entangled pairs, and then one particle going here, one particle going there, they are entangled. And then they just used a lot better detectors here, which are transition hedge detectors, where you have a superconductor, and if a photon comes in, it changes the temperature of the superconductor, and therefore the resistance for electronic signals going through the superconductor. And in this way you can detect even number resulting photons coming into the detector. This is enough to close the detection loophole with photons. You just use better detectors. The problem, apart from having better detectors, you also have to collect the photons really well. And so if you have your entangled source and you generate one pair, then you have to make sure that both of these photons, these entangled photons, are actually detected with as high efficiency as possible. And typically, at least in the experiments I worked with, this was far from going to happen. So you have your source, and then you have to couple these photons coming out from the crystal into a fiber, and the efficiency for doing that is, I don't know, 20% or so usually. And well, let's say 40% if you're good, and then you have the detector, which also has 60% detection efficiency, and then that degrades the whole efficiency down to 20% or so. 40 if you're really good at ironing everything and having good detectors. And here they had efficiencies of more than 90% for the detectors alone, and also very high detection efficiency. And to close the detection loophole, you need efficiencies higher than 72% or so.
You have perfect fidelity 66 or 60 depending on the source, and in this case, in the standard noise you have is 70%.
Yeah, it's just this one was built. So there's one more loophole. So that's the freedom of choice loophole. So I was talking about the locality loophole. Locality loophole means just that the choice of my measurement is random essentially, and the choice of the measurement on one side is not influenced by the choice of the measurement on the other side. The freedom of choice loophole also means that puts the particles that I generated my source already, when I generate them, know what I'm going to do with them later on, and measure at the field vectors. So usually in all direct experiments, even in the one that close the entanglement loophole, like this one, this was not the case. So these were not spatially separated. The events where the particles were generated and the events where I made the choice for the so the photons could have known beforehand more than they should know. So if they have hidden variables in them that determine the measurement outcomes, these hidden variables could have already have depended on some choices made by this photon. And this is not the case in this experiment where all the events were spatially separated. So at some point the photons were generated. The choice which measurement setting was to be made by Alice was already made before that. So the emission event at the source was independent of the choice I made here. And then my photons traveled out to Bob. And also Bob, even before this information about the my setting here could reach him, he has made his choice, what he is going to measure. And then the actual entangled photon reaches him, and he applies the measurement. And so the setting at A and B, that is in Bob, they are completely independent, and the source doesn't know what they're going to do. So that's the freedom of choice loophole. But this, I think it was also over long distances in order to close this locality loophole on the one hand. And on the other hand, the distance chosen here, and like the Italian group always does these experiments between the environment and Nordita, that's not just because it's beautiful environment for experiments, but also because the distance between here is just right. It's more or less the same distance, basically the atmospheric equivalent of just taking a laser and shooting it up to the ISS. Actually, atmospheric equivalent is even less. That's the right distance. So that's 140 kilometers, and typically the ISS is, the orbit of the ISS is about 140 kilometers away from the ground. So that's also at the same time testing the optical system that we could in principle do that if we would go to space. And also one of the stations here usually is an observatory they have there. So this observatory they use for this experiment, they use it horizontally for that experiment, but we really could also just point it up to space and track the ISS, for example. So the thing is with this experiment that the time between, okay, I create my entangled sources, my entangled photons, and I make the choice of what I'm going to measure. This time is very short. It's only 4.3 microseconds. And so the thing is, what if earlier events already than that influence what happens at the source and in this experiment? What if a conspiracy between the two photons was already made earlier than these 4.3 microseconds in the past? And there was a suggestion this year. I think it was published this year, suggestion from that. So the idea there is, okay, you can push this decision, what's going to be measured, further and further in the past if you base the choice you make in your measurements on things that happen far, far away, like quasars. So essentially you can take two telescopes, point these telescopes point one in this direction, the other one in this direction, and focus each one of them at a very distant quasar and look at random signals coming from there and base the choice for your bed experiment on the random signal coming either from that quasar or from that quasar. So if you then still assume that, okay, these measurement settings are in some way correlated, then this could be a conspiracy that has been going on for a very long time. And this is not my way of saying I do believe in God, it's just saying okay, I think that's ridiculous. Okay, so I already talked about that Tanner group is doing these experiments between the two islands with this 140 kilometers distance, and in principle that's the distance you need to go to space. So in principle, the technology over the last years has been developing in this direction since 2003 or so, I think. And so by now I think we are ready to go to space, as I will show in the next slides. It's just a matter of money at the moment. Money and political will. And so that's just some experiments over the last years. So that's actually one I was included in back then, like the first two. And then I was still in the Italian group. So this was a free space experiment over 600 meters, where we showed that we could have the entanglement source on one side of the Danube, then shoot one photon over to the other side, and just via telescopes, catch it again and violate the inequality on that side. So that was the first free space experiment over a significant distance outside the lab where the inequality was violated. And later on it was also first teleportation over a really long distance. Before that there was also long distances, but in fiber coils and that. And these experiments then went on and on over longer and longer distance. Like I think it was the Landwater group in Munich that did the free space experiments between two mountains over 20 kilometers or so a few years later. And there were experiments with fibers, of course. With fibers you can go over 100 kilometers. With free space, we also did an experiment in Vienna between two stations in Vienna, about 40 kilometers distant. And also, it was also hooked up in collaboration between Vienna and Italy, where they just showed that in principle, if you would send a single photon from a satellite down, you could detect it. So what they did was, there was this small satellite floating around in orbit, which was not a very exciting satellite. It was just a sphere covered in mirrors. So if you shoot a laser up at this sphere, it will reflect light and you can catch that light again. And what they did was shine a laser up with just enough power that they reflected. When it reaches this satellite, the power coming back from the satellite is just on a single photon level. So this was just a technological demonstration that you could catch a single photon from space, from lower Earth orbit, let's say. And then, yeah, then there started to come these experiments between the two islands. And it's more the same, which is getting better and better, more distances, doing different experiments over these large distances. I still have 10 minutes, so I don't have to go back. Okay. So,
sure. I'm just curious, what is the advantage of going to space over just going between two islands? What is there?
It depends on the experiments you want to do. On the one hand, there's a very practical aspect to it. If you use quantum entanglement as a resource for applications like cryptography or stuff like that, or if you want to connect distant, not yet existent quantum computers, but in the future at some point, fibers limit how far you can go. So that's typically on the order of 100 kilometers, maybe a few hundred kilometers. And if you want to go from Vienna to Australia or from here to Australia, that's too much for fibers. So it's easier to use satellite communication as people do it now for classical communication already. And it's easier with classical communication because you can always amplifies the realism as well. But with quantum signals you can't amplify them. So if you can get rid of sources of attenuation, then you should. And for space, if you go directly up in space, you do not have attenuation, unless, well, what you do have is, if you have two telescopes, you of course have to couple all the photons. You shoot from one side to the other. So that's the limitation in space. But in principle, for example, you could imagine that you have a ground station communicating with a satellite, and then the satellite travels on, and then it communicates with another ground station. As long as you trust the satellite, you can make a secret key, for example, between two spots on opposite sides of the Earth. So that's the practical point of view, and the fundamental point of view is, of course, you would like to test quantum physics over longer and longer distances, maybe between objects going at different speeds, so you have to take into account theory of relativity too, and so maybe there's going to be deviations at some point, or maybe you're just extending the parameter range over which you know that quantum physics is good.
Just real minor. When they do the non-locality for these free space tests, do they have to correct for things like, you know, the index or a fraction of error?
In some points, yeah. So you have tracking systems. So usually when you do experiments like that, you have the single photons going, but at the same time, you often have just a normal laser going the same way, and you use the normal laser to analyze what's going on in the air and then correct.
But do you have to figure that in on like the timing?
On the timing,
so you're delayed by, you know, what is it, a few tenths of a percent?
Usually I think
versus speed of light in vacuum.
The time difference is not so large, but in principle you would have to include it. It depends on the experiment you're doing. If you just do a bell measurement, then the timing is not so critical. If you're doing teleportation, so then the timing starts to become very critical. And especially if you want to then, let's say, what we usually do for example, if you do teleportation, then you have two entangled sources, and then you have to overlap two of the entangled photons at a beam splitter, and the distance those photons travel has to be matched by a few micrometers or so. It depends on your photons. And this poses much tighter restrictions on what you're doing. But in principle, yes, you can shoot. The lasers they are using, you cannot use them for timing, really. Because they are CW lasers, you would have to use pulse lasers for timing. But what they do is to synchronize the two computers with GPS. And also Ethernet, just being connected to atomic clocks somewhere over the Internet. And combination of GPS and Internet timing gives them enough resolution to do most of the experiments. Not much more. So yeah, that's anyway why you would possibly want to go to space. The one thing is, of course, this communication thing, just a practical aspect of it. And if you go to longer and longer distance, at some point, different aspects of physics start to come in. Relativistic, special relativity for long distances, and maybe even general relativity. But obviously, that's to have entangled photons going from Earth to Jupiter or something like that. That's a very, well, it's still far in the future. By now, I mean, optical communication has been shown to work pretty well up to distances of the moon, at least for classical communication. For quantum communication, the limits are stricter than that. But in principle, it should be possible. And if you're just in space, then it's much easier, because if you go away from Earth, then you always have to go through the atmosphere. And if you start the laser beam on Earth, then you always have what people call the shower curtain effect. That if you go through the atmosphere, then small fluctuations in the air will make fluctuations in the beam, and after a few million kilometers, these fluctuations get really, really large. So shower curtain, because you can be really close to the shower curtain, but people outside still don't see it. And that's the same with the atmosphere. obviously, what would be really cool is, as far as freedom of choice case, for example, I talked about these different quasars here and there, and to make the choices of the experiments independent. But obviously, what would be really nice to do is to have one astronaut sitting there and another astronaut sitting there and making a choice and doing that experiment in real time, flipping the polarizers every second. Good. And now just to go into detail a little bit. So that's mostly because I'm in Vienna now, mostly what the Vienna group is doing in this direction. There's also efforts in Canada, of course, with Radio France Institute. Thomas Chennewan is working on that. Also having satellites in space, having QKT systems, entangling places on different spots on the Earth, far away from each other. And the Vienna group has been on that since 2003. That's when I was doing my master thesis there. And Rupert Wilson has been doing that for the last 12 years now. And the idea at the moment is to put an entangled source, that's what they want really, is to put an entangled source in space on the International Space Station. And they have everything planned out. In principle, they could do that already. They just need 70 million watts. And so far, nobody gave it. At least Austria is maybe too small in country to spend 70 million. It's also a huge international collaboration, so right now they're working together also with people from China, and China has a lot more money than Austria, and to be able to fly that in the next 2 years or 3 years, so we are working on that at the moment. But for the ISS, that's at the moment, that's a good plan, and they have everything designed, but let's see if it will really happen in the next year. And the idea there, that the good thing about that is that it really would have an entangled source in space. It would be able to create directly entanglements between very distant spots on Earth, many thousand kilometers. Well, yeah, not many thousand kilometers, but thousand kilometers. As a first test at least. Obviously, the good thing about the ISS is also that you have humans there which can interact with the source, which on satellites the whole thing would have to work automatically, so you wouldn't have to have as much choice of what to do when you make changes. Good. A much cheaper version would be to have just a single downlink, and actually there's a window on the ISS where you can just put a camera in front of the window and collect photons coming from Earth or shoot photons out from satellite. So the cheapest version would be to have an uplink, so we shoot entangled photons up to the ISS, make measurements there, and maybe create an entangled link. Just a quantum cryptography between ISS and ground, and then ISS can fly on somewhere else and make another link between a different ground station and ISS. Obviously, you have to trust the astronauts in this system. Still cheaper versions to use a CubeSat. So CubeSat is this concept of where you have these small, like cubic decimeter sized satellites, and you can also stack together more than one of them, and then you shoot them with a typical Ariane rocket or something. The Ariane rocket starts, and it has on the tip it has these CubeSats, and it just shoots them out of the tip of the rocket, and once it's in space. Okay. That's actually from Ray School. I stole a picture from you. And that's it more or less. So the conclusions are, I don't really think that you can apply the concept of reality to microscopic systems. I wouldn't call things non-local, I would stick to non-realistic, but that's a matter of choice. And seeing all these experiments that have been done closing the loopholes, the air is really getting thin to keep up these views, having loopholes, keeping up local realism as a valid option to explain what's going on in the world. And I've shown you hopefully a few ideas what's going to happen in space, and that the technology is ready for doing that, more or less. So So let's see where things go from there.